Hello students, welcome to the lecture series of DC machines and transformers. Now in today's video lecture we are going to discuss about DC motors. So already in the first part of module 1 we had a discussion on DC generators. Here it is DC motor. So DC machine can be used as generator or motor, so that the construction wise the DC motor and DC generators are same. So there is no need of separate constructional details to be discussed for motors, since at the time of DC generator discussion we have seen the construction features. The same machine can be used as motor. So when operating as generator, we require mechanical input and the flux that will generate EMF. But the same machine, if you want to operate as a motor, it is to be connected with the electric supply, that is electrical input is to be given, which supplies the current and it develops the torque so that it is running. We will get a mechanical rotation as output. Yes, any motor will convert electrical energy to mechanical energy. When current carrying conductor is placed in a magnetic field, it experiences a mechanical force whose direction is given by the Fleming's left hand rule. So this is the principle of DC motor. So when a current carrying conductor is placed in a magnetic field, it experiences a mechanical force. It produces some force, and the direction of that force can be found from the Fleming's left hand rule. So the function of commutator in motor, the commutator's function in generator is the rectification. It is mechanical rectifier which converts the bidirectional current into unidirectional, whereas here it is serving the same function. Here also it is reversing the current in each conductor as it passes from one pole to another. When it is under n pole, it is in one direction, right? So when it is in a s pole, that is south pole, is in other direction, right? It helps to develop a continuous and unidirectional torque. So here the commutator is used to produce unidirectional torque, whereas in generator it is to used for getting unidirectional current. Yes, you can revise your Fleming's left hand rule. So in a left hand thumb, forefinger and second finger, we can fix the movement of conductor and field, direction of field and direction of current. So when all three fingers are perpendicular to each other, if we know two different things, other thing can be found. Here in this case, the field, the magnetic field direction was known, and the current direction is known. So the unknown value here is the movement, the rotation. So that can be found from applying, found from Fleming's left hand rule. So force on a conductor with and without current. So here mechanical force is exerted by the conductor always acts in a direction perpendicular to the plane of the conductor and the magnetic field direction. Direction is given by the left hand rule. Yes. So we are explaining that Fleming's left hand rule. From the Fleming's left hand rule, the force, magnetic force exerted will be perpendicular to the plane of the conductor and magnetic field. So if either the direction of current or the direction of field is reversed, then the direction of force is also reversed. Whereas if both current and field are reversed, the direction of the force remains unchanged, meaning that the field winding which gives the field for your motor, magnetic field, magnetic flux, and the conductor is carrying current, right? That armature conductor, the armature current direction is the direction of current. So if you change the direction of current, you can change the direction of rotation, or if you change the direction of flux, then also you can change the direction of rotation. If you change both current and magnetic field, then the direction is same. Okay, so in DC motors, if you want to change the direction of rotation, you have to change either the field direction or the armature current direction. So this force on a conductor is given by BIL newtons, where B is the magnetic flux density, and which is given by Tesla or Weber per meter square. Flux per area, B is the flux per area, magnetic flux density, which is equal to flux per area, and the unit is Weber per meter square, also Tesla. It is also called Tesla. So here the DC motor circuit diagram, which shows the shunt motor. There is a field winding which is in parallel with the armature, and we are giving supply voltage V to the armature and field winding. So I is the current, I or IL is the line current drawn by the motor, and in that line current it is given to armature and field. So the field usually having high resistance, so this field current is less. Armature will have low resistance always, so the armature current will be high. So the total current IL, the line current, is equal to IA plus ISH. And we have back EMF in motor, which is opposite to the supply voltage. So that EB is represented with the direction which is opposite to the voltage. So what is back EMF? Back EMF or counter EMF, which is direct opposite to the supply voltage, which is another voltage in your motor, which is direct opposite to the supply voltage. And that back EMF is proportional to the speed, so that if speed increases, back EMF increases, and armature current decreases. If speed decreases, back EMF decreases, so armature current increases. It acts like a governor for motor. And the voltage equation of DC motor, which is EV plus IaRa. You are giving V supply voltage. In that V supply voltage, due to armature resistance, there is a voltage drop, that is IaRa. So V minus IaRa. So against that V minus IaRa, the EB is produced. So that EB is equal to V minus IaRa, or V is equal to EB plus IaRa. That's it. We will see in the next session.